Section 16, and closely related Section 17. We've talked about a couple of ways to compare variables. One of the ways we talked about was in Sections 14 and 15, where we were comparing two population proportions or comparing two population means. Another way was when we did the paired samples in Section 19. Before and after, that kind of thing. In all those cases, they had to be the same kind of variable to compare them. Gallons less than other gallons, degrees Fahrenheit more than other degrees Fahrenheit, and so forth. But there is a third way that we can compare two variables, even if they're very different kinds of variables. The archetypal example here would be something like the ages and heights of various trees. So, correlation and closely related in Section 17, linear regression, goes something like this. First of all, we're not doing any inference on correlation or linear regression, not in this course. You can, but we're just not doing it for time reasons. What we're doing is more akin to analyzing data as we did back in Section 2. So, in other words, we're talking about analyzing the sample, finding numbers for the sample, but without making necessarily any broader generalizations to the populations. And this is very important because the sample you have may be typical or it may be atypical, so you do want to be a little careful about generalizing, as we've already seen. So suppose you wish to compare two quantitative variables on the same set of individuals. For instance, ages and heights of a lot of people, something along those lines. The idea here would be that you want to make some conclusions, either about the individuals you happen to have, or perhaps you are trying to make generalizations. For the individuals you happen to have, do the older ones tend to be taller? That kind of thing. Examples: amount of alcohol, body temperature. More alcohol, what effect does it have on body temperature? Corn per acre planted versus corn per acre yield. Time studying versus grade on exam. Notice again that they can be two very different kinds of variables. Hours, percent on exam, weight and height. How do people's weights relate to their heights? That kind of thing. Height at age 6, height at age 16. Are people that tend to be taller at age 6 tend to be taller at age 16, or is there no relationship? If you're talking about a couple, the height of the male, the height of the female. Note the direction of the arrows. This is very important. Sometimes, not always, sometimes we're thinking of some kind of input-output or before-after relationship. Some kind of I don't want to say causality because that may not necessarily be the case. If I use the word influence, then it sounds a little bit more neutral, but it's really saying the same thing. But of course you get the idea. The amount of alcohol logically comes prior, and the body temperature is reacting to it. Responding, if you will. Corn per acre planted comes chronologically and logically before corn per acre yield. Time studying comes chronologically and logically before grade on the exam. Height at age 6, height at age 16. But for other examples, you can do it in either direction. How does weight influence height? How does height influence weight? And likewise with couples. The arrow represents the direction in which we might consider there to be some kind of influence. Which variable we're thinking of as coming first? Which variable explains the other? The word you want to avoid here is cause. Cause is beyond the scope of statistics. Causation has nothing to do with mathematics or statistics. As we've already seen, all we can do is establish trends or patterns in the data we happen to have. They can tell you that things are worthy of further study, or maybe that they're not worthy of further study. But the causation comes into it. Science, philosophy, whatever, logic, where the math ends. All that the math can do is tell you that there's an interesting relationship that might be worthy of further study. Nevertheless, we can talk about how amount of alcohol potentially influences body temperature. Whereas it wouldn't make sense necessarily to talk about it the other way around. You can talk about how time studying influences grade on exam, whereas it might not necessarily make sense to do it the other way around. Now the arrow, the direction of the influence, which variable comes logically first and which variable comes logically second, has nothing to do with what we're talking about at the moment. It is completely irrelevant for correlation, but it will be very important for the next section, linear regression. So because I'll be continuing a lot of the same examples, wherever possible, I'll think of the variable that logically comes first and then the variable that logically comes after, but it doesn't really affect any of the calculations we're doing in this section. A scatter plot is a way of relating two variables. For instance, in this particular example, we have command training score. We have two different exams, command training exam and Kobayashi-Maru exam, and we can see how the scores generally line up. This is the general idea, of course, is that the dots represent the horizontal location and the vertical location of one particular individual. So, if you're graphing ages and heights of many people, then maybe age is horizontal and height is vertical, so that an individual who falls here is this old and this tall, and so forth. And again, notice that for the long run, it won't matter for this section, but for the long run, if there is a variable that is coming logically or chronologically prior, then let's put it horizontally. Maybe it makes more sense to think about how age goes in and height comes out. So we'll put age horizontally and height vertically. For the long run, it doesn't affect what we're doing in this section, but if there is an input-output type relationship, think of the one that goes in as the horizontal and the one that comes out as the vertical. In this particular example, it doesn't really matter. We're just talking about two different Starfleet exams. For instance, this particular individual got, it looks like about a 95 on his command training score, and it looks like about a 97 on his Kobayashi-Maru score. And thus you can see some general patterns. Individuals that did higher on the one exam tended to do higher on the other exam. Individuals that did lower on the one exam tended to do lower on the other exam. This individual got a 75 command training score and maybe about a 74 Kobayashi-Maru score. This individual also got a 75 command training score and slightly lower Kobayashi-Maru score. Notice, by the way, that this is not like graphing in the mathematical sense. There's no reason in the world that you couldn't have individuals that have the same command training score but different Kobayashi-Maru scores. There's no reason why you couldn't have individuals that were the same age but different heights, or the same height but different ages. So you can have dots next to each other or directly above and below one another. There's no reason in the world you couldn't have that. But again, once you've got the scatter plot, you can see the general trend of the relationship. Here there's what we might call some degree of positive association. The tendency is that for the individuals who have a higher command training score have a higher Kobayashi-Maru score, although there are some exceptions in this territory here who did very low on command training score but very high on Kobayashi-Maru score. Nevertheless, we can see the overall trend from low going with low to high going with high, with some interesting exceptions. You can see that there's a tendency for cadets who get higher command training scores to get higher Kobayashi-Maru scores. It's not absolute, and there's some exceptions, but you can definitely see the trend. This is what we call positive association. Positive association means that there's a tendency for individuals that are high in the one variable to be high in the other variable. High numbers go with high numbers, low numbers go with low numbers. They're going in the same direction. Negative association would be the opposite tendency for individuals who get very high scores in one variable, get very low scores in the other variable. For instance, maybe it's the case that alcohol lowers body temperature for the sake of argument, so that higher amounts of alcohol give you lower body temperature. and so on and so on. In most of these other examples, we're probably looking at positive association. Now, bear in mind that we pick our scales appropriately. You know, it wouldn't make any sense to start at 0 horizontally. It wouldn't make any sense to start at 0 vertically if all you're going to do is create a lot of empty space. Nevertheless, you can pick radically inappropriate scales. So in this case, if we start the Kobayashi-Maru scores down near 0, then all we do is scrunch up the previous picture. It's exactly the same graph as far as that goes, but it's a little bit more scrunched up. So we'll throw in this cadet who did very high on the command training score, but very low on the Kobayashi-Maru score. So the attempt to accommodate this obvious outlier in the data scrunches up the rest of the picture. The rest of the picture is exactly what it was before. It's just scrunched up because we're expanding this vertical scale to accommodate the new individual who wasn't present in the previous set of data. And I'll leave it to your imagination who this is. Notice that the attempt to accommodate the new outlier forces the rest of the picture to be scrunched up. A scatter plot plots one variable horizontally, call the horizontal one x, and another variable vertically, call the vertical one y. It doesn't make a distinction between which is which. Notice that if we plot things the other way, take the simpler example, notice that if we plot things the other way, putting Kobayashi-Maru here and command training vertically, then all it's going to do is basically amount to a diagonal flip of this entire picture. The trend remains the same, you're just displaying it differently. So which variable is displayed horizontally and which variable is displayed vertically is a very cosmetic thing. It only affects how you're viewing the picture, but it doesn't really affect anything important. Nevertheless, for the future, not for this section, if there is one that you're thinking of going in, call it X, put it horizontally. And if there is one that you're thinking of cutting out, being affected by it, call it Y, put it vertically. It'll be important for the next section. Here we go. Positive association is a tendency for large values of one variable to go with large values of the other. They're going in the same direction, an upward trend, if you like. As you look to the right, the dots tend to go upward. Negative association is a tendency for them to go in opposite directions. Large values of one variable go with small values of the other. Now, it's important to note that association is something that we pick off the picture. So it's very subjective. It's something that you see by eye, the general trend of a picture. And as we've noticed in earlier sections, whenever we're making observations from a picture that we've drawn, observations that you make by eye, they are very subjective. Association is a very subjective thing. It's got to do with the trend in the picture. Correlation will be closely related, but that is a computation. The correlation between two variables, first of all, is a number. It's something that you compute. The correlation between two variables is a real number between -1 and 1, whose absolute value represents how lined up the dots are. Ultimately, all we're going to be doing with scatter plots is the only real purpose they serve for us, apart from you can notice some trends, we're not going to really be drawing scatter plots. The reason I talk about scatter plots is simply to help you wrap your mind around correlation. Once you've got the scatter plot, the correlation represents how lined up the dots are. If you want to jargon it up a bit, the strength of the linear trend. So the size of R, lose the sign on it, and the size of R represents how lined up the dots are, the strength of the linear relationship. If there's an upward trend, if there's some degree of positive association, then R will be a positive number. If there's a downward trend, if there's some degree of negative association, then R will be a negative number. So association and correlation are closely related, but association has got to do with the picture. Correlation is an actual computation. In other words, if the dots are completely lined up in a perfect line, then r will be exactly 1 or negative 1. It'll be 1 if it's a rising line. It'll be negative 1 if it's a falling line. However, the numerical aspect of r has nothing to do with steepness. It has to do with how lined up the dots are. That is to say, r is not slope. R is in no sense of the word slope, apart from the obvious. If it's a positive number, then there's an upward trend, largest going with largest, smalls going with smalls. And if it's a negative number, then there's a downward trend. Notice that slope is a very artificial construct in context because you can play around with the scales. The line that best goes through these dots, well, it looks on the steep side, but here anyway, it looks on the shallow side. That's a very cosmetic thing. You're just playing with the scale. So we're not for the moment talking about slope, apart from the fact that if there's an upward trend, r will be positive. If there's a downward trend, r will be negative. The size of r has to do with how lined up the dots are. If r is very close to 1 or negative 1, then the dots are very lined up. If r is very close to 0, then the dots are very unlike a line. That could play out in all kinds of ways, but the obvious example would be just a random cloud of dots with no hint of an upward trend or a downward trend would have a correlation very close to 0. And this is just saying what I just said there in so many words. So before we actually compute correlation, some observations about it. Correlation is always between -1 and 1, and it can always be computed, with one sarcastic exception that we'll talk about a bit later. But if you have two actual variables that actually vary, then correlation can always be computed, and it'll always be between -1 and 1. Correlation does not change if we change units. The correlation of height in feet and age in years is exactly the same as the correlation of height in inches and age in days. Numerically speaking, if we multiply every number by 12 and then recompute correlation, it's not going to change our answer. Alternately, if we multiply every number by 365 and recompute correlation, it's not going to change our answer. Correlation does not care how you measure things. It takes no account of the units you use. And that's kind of obvious if you think about it. If you've got ages and heights, let's say for the sake of argument, then multiplying every one of these by 12 to turn, let's say, feet into inches is only going to stretch out the scale 12 times, which, yes, will affect the picture if you overlay them, but again, you could physically make the tick marks 12 times closer together. It's a very cosmetic thing. It's got nothing to do with anything we're talking about. How you measure things has nothing to do with the computation of correlation. Correlation doesn't care which variable is which. The correlation between age and height is exactly the same number as the correlation between height and age. In other words, physically flipping the picture, as I was talking about a moment ago, doesn't change how lined up the dots are, which is what correlation measures. Correlation does not care which variable is which. And there's nothing in the math, as you'll see in a minute, that could possibly care which variable is which. Here's the book way of computing correlation. As always happens with these formulas, the one that looks easy to use is the one that's really nasty to use in practice, and the one that looks very complicated is a lot easier to use in practice. So I'm not going to dwell on the way that the book computes correlation, apart from to notice that we are standardizing the variables here. Subtracting the mean and dividing by the standard deviation, remember, is the way that you make units irrelevant, as we've talked about since section 2. So that's just justifying this point here. However, because you can see, typically the mean is not going to be a nice number. If the mean is 5.738, then not only is subtracting it from everybody going to be tedious, but you're going to lose accuracy. Rounding, rounding, rounding. As always, the more often you round and the more grossly you round, the more off your answer is going to be by the end. So a way that is a lot easier to use in practice, but of course it looks a lot worse. Theoretically, that is, algebraically, it is exactly the same number, it is exactly the same computation. But because it involves a lot less rounding and a lot less tedium, it's a lot easier to compute, and it will be more accurate in practice because you have to do less rounding in the middle of the process. Some of this may look very familiar. What we have here is 5 underlying pieces, 4 of which we've already talked about in the past. I think I have a blow up of this. There you go. So here's how you compute correlation. You do it in 3 stages. Add up the x's. We've talked about that before. Add up the y's. We've talked about that before. Add up the squares of the x's. We've talked about that before. Add up the squares of the y's. We've talked about that before. And the new bit would be right here, which is multiply them in pairs and then add them up. So we have 5 underlying pieces: the sum of the x's, the sum of the y's, the sum of the x squares, the sum of the y squares, not pictured, and the sum of the xy pairs. From that, you get the 3 major pieces, 2 of which we've talked about before. This creature here may look familiar because it's the numerator of the computation when we went to compute standard deviation. Correlation is very closely related to standard deviation, so it's got a lot of the same computations going on. This is the creature we've talked about before. Add up the x's, square them, divide by n, that is the number of individuals, the number of pairs, the number of x's. Add up the x's, square them, divide by n, subtract it from the sum of the x squares. And we'll call this creature SSX. Likewise, not pictured, do the same thing for y, so exactly the same computation. SSY is add up the y's, square it, divide by n, subtract it from the sum of the y squareds. The new bit is an adaptation on the same theme. Instead of multiplying the x sum by itself or the y sum by itself, we multiply the one by the other, and then do the same dividing by n. And instead of multiplying each x together or each y together, we multiply the xy's together and then add them up. So this is just a variation on the same theme. That creates these 3 major pieces: SSX, SSY, and SSXY. I'm kind of mixing my capitals and my lowercase here, but don't worry about it. And then on the 3rd level, you go to compute correlation by doing this divided by the square root of SSX times SSY. Notice, by the way, that you don't have to do an awful lot of rounding here. If you've got nice numbers, then the sum of the x's, the sum of the x squares, the sum of the y's, the sum of the y squares, and the sum of the xy pairs are all nice numbers. You don't have to do any rounding. So worst case scenario, you're dividing by 13 here, which makes this calculation a little ugly. But worst case scenario, you've only got 3 ugly numbers to deal with, and then you can just put them together. So there's a lot less rounding in practice using this version of the formula. We'll do some examples. Note that SSX and SSY are simply the numerators under the radical when we computed standard deviation back in section 2. SSXY is, yes, just another variation on the same theme. So there is the theory, and I'll do a couple of practice examples in the next video.